Haripriya, what about other people? Manasvi.
Yes, sir.
It is lecture number 2 in unit number 4. Okay. And we talk about circuit designing. Okay. Circuit designing. So here what we have seen in the last class, we have recap. Let us recap what we have seen. Based on NMOS technology and CMOS technology, we have realized is based circuits have been done. Circuit design by using these technologies. Various circuits have been realized. Various circuits have designed. Okay, so out of all those things, we have seen that what we have seen, NOT gate that we have seen. Okay, and the second one is NAND gate that we have seen, and we have seen NOR gate, and we have seen XOR gate. Okay, so a little bit information is required for this one. Before going to that one, let us evaluate today we are going to evaluate some performance parameters of a circuit. Let us look at. Okay, so for example, so now we are going to see performance parameters. Parameters calculation. So very simple thing that let us consider, which are based on sheet resistance and the capacitance. For example, I have an inverter something like this. Okay, so For example, this is a 4:1 ratio I have given. It is 1:1 ratio I have given. For example, A, and this is Y. Okay, if I ask you to calculate what is the power dissipated by this particular inverter, what is the power dissipation that can be seen for this one? So if you want to calculate the power dissipation, we do one thing. Okay. So let us see the power dissipation. In this case, what is the power dissipation formula? Anybody can guess? P is nothing but V square into R. Sorry, V square by R. Can we write like this? Static power dissipation. P is equal to V into R. So since we know that very well, P is equal to voltage into current, right? So I want to calculate some of the current based on this one only. V by R, I can write it there. So therefore it becomes V square by R. So it is suitable to do it in this particular scenario. Okay. So how do we calculate the V value? V value, we know that. So V stands for VDD. So here V is equal nothing but VDD, which is equal to, for example, 5 volts. Let us consider 5 volts. Okay. What about R? What about R? So R is nothing but R on. R is nothing but R on. So what is the R on for this particular network? As we all of you know that since a very small calculation is required, what is that? We know very well. The moment if I'm saying that 4:1, which means that what is the minimum transistor dimension? 2 lambda by 2 lambda. Therefore, this is actually the length to width ratio. This is also length to width ratio. So length is normal transistor's dimension is 2 lambda by 2 lambda. Length to width ratio. This is so length to width ratio. So length is multiplied by 4 times. 4 times of 2 lambda is 2. Width is also, width must be implemented by, multiplied by 1 into 2 lambda. So this is actually 8 lambda into 2 lambda is the dimension of this transistor in terms of the lambda. What about here? 1 into 2 lambda into 1 into 2 lambda. So therefore it is 2 lambda by 2 lambda. So we know the dimensions of the transistors. ZPD is nothing but, how do we calculate? Sorry, I can say that the resistance offered by pull down network, PD pull down network is equal to, what is the value? We know that ZPD into RS, sheet resistance. What is this value? ZPD on 10,000 by 1 K. ZPD is nothing but length to width ratio for the pull down network. Therefore, 2 lambda by 2 lambda is multiplied. What is the sheet resistance of a channel, NMOS channel? It is 10 to the power of 4 ohm per square. We know very well. Okay, therefore, this is value is equal to 10 kilo ohm. So this is how we can write it, kilo ohm per kilo. Okay, so this is how we can calculate for this one. What about this upper transistor? What about the upper transistor? This is pull up, which is equal to ZPD is ZPU is multiplied with RS. What is this value then? 8 lambda by 2 lambda is multiplied with 10 to the power of 4 ohm square. Okay. So what is this value then again then? Now here it is actually 40 kilo ohm per square. So therefore, what is the R on now? R on is nothing but adding up, because both are connected in series. Pull down network plus pull up network. So it becomes 50 kilo ohm per square. So this is called R on, right? So therefore, what is the power consumption of this one? So therefore, power dissipation or power consumed by this inverter is PD is equal to V squared is multiplied with 1 by R on. So this value is equal to VDD squared. So the phi squared is multiplied with 1 by 50 kilo ohm per square. So we calculate this one. What is the value there? You can do this one. Okay, 25 divided by 50. So 25 divided by 50 and 10,000 Babu. You can do it. I don't want to waste my time. Okay. So therefore, this is 25 divided by 50 kilo. So what is this value then? 2 times. Okay. 0.5 milliwatt power. So 0.5 milliwatt it will be. Okay. Something like that. So this is how we have to calculate the power consumed by this one. By the way, what is this capacitance offered by this one? What is the capacitance that we can see at the input? So therefore, the gate input is equal to 1 square Cc will be there. Okay, before going to that, yeah. So it is 1 square Cc at the gate input. Okay, 1 square Cc will be the capacitance for this input. Therefore, the input capacitance is equal to 1 square Cc. So that's what we observe. So the resistance and capacitance multiplication will give you the delay of the network. So the delay of the network is nothing but delay. So delay will be calculated by resistance into capacitance. RC delay that we are interested on. Therefore, R on is multiplied with capacitance. So we have to calculate the capacitance of the gate. So at the input delay that I want to calculate. Okay. So therefore, the resistance into capacitance that we have to calculate. Okay, I think it's at the input side, right? So better we have to calculate the pull down network related capacitance that we can calculate of A. So A is the input capacitance. So like this, we have to calculate of course, it's depending upon different parameters, but for the time being, just I won't want to calculate this one for the time being because its various factors will be depending upon that one. So straightforward question, straightforward way to calculate the power dissipation and input capacitance of the gate is in this way. Okay. For example, I'll give you a piece of layout. Okay, let us calculate the power consumed by that particular transistor. Okay, so another example, let us consider power calculation for an inverter and a transistor. We'll write a transistor. For example, something like this. A piece of for example, this is a layout that we can see here. Okay, so so therefore, this is what a piece of layout. So this is an NMOS enhancement NMOS. It is a depletion NMOS. So depletion NMOS. Okay, so normally we know that depletion length, the depletion mode type of transistor length is more than that of the enhancement type NMOS transistor. So how do we calculate this one now? Okay, so what is its dimension? Its dimension is 16 lambda into 2 lambda. So therefore length to width ratio. So now this value is 2 lambda by 2 lambda, length to width ratio. So we already know how to calculate this this one. What I'm going to do here is that what if I reduce the width of the transistor by half? The question is that what if you reduce the length of, if you increase the width of the channel, Or maybe, of course, by varying the different lengths of the transistors, what may be the effect that we can see? That's what the question is. So therefore, the question is that, just I want to give you one question here. So what if I reduce the length of the, width of the pull down network? If I reduce the width of the pull down network by half, what will happen? So let us calculate what is this input capacitance and output capacitance of this one, and we will go for the next level. Okay. So simply let us consider this one. What is the power dissipation for this piece of layout? V square into 1 by R on VDD square into 1 by R on. It's 5 volts. 5 square into what is R on? So what is this value? 8 is multiplied with 8 and 2 8 something. 8 into 10 to the power of 4 plus 1 into 10 to the power of 4. Okay, what is this value then? 25 divided by 90 kilo ohm per square. So this value becomes, what is this value? Can anybody guess what is this value? Okay, some value will be there. I'll do the calculator. Cal open 25 divided by 90. So 0.27 milliwatt of power that can be seen. I'm taking another piece of layout, which is having, this is the one. For example, a piece of layout is something like this. Okay, so what is happening here is that, see, the length of the depletion mode type of transistor is somewhat decreased by something like this. Of course, it may be a depletion type mode transistor, whatever it may be, the transistor dimensions are that one. And this is also 2 lambda by 2 lambda. So now the width is width of the channel is varied, something like this. 4 lambda I have considered. Okay, what will happen in this case now? So what is this value? It's 8 lambda into 2 lambda, length to width ratio. What is it here now? Length to width ratio is 2 lambda into 4 lambda. 2 lambda into 4 lambda. So width is, I have taken something like this. So what is this value then? R on, power dissipation by the circuit is equal to PD. Don't write PD. Power dissipation by this, simply VDD square is multiplied with 1 by R on. So 5 square is multiplied with 1 by R on stands for 2 lambda, right? So it's a 2 lambda. It's a 4 into 10 to the power of plus 4 plus, and what is this value? 1 by 2. Okay. So 2 lambda by 4 lambda. 2 lambda by 4 lambda is 0.2 into 10 to the power of 4. So what is this value then? So 5 square is multiplied with 0.54. 1 by 40 kilo plus 0.5 kilo. Okay. Sorry, it's not 0.5 kilo, right? It is 0.5 into 10, 5 kilo, right? It's a 5 kilo. So 5 kilo ohm. So its value becomes, what is this value? 5 square into 1 by 45 kilo. So we have to calculate this one, 25 divided by 45K. So what is this value? 25. 45. So 0.55. So 0.55 milliwatt of power, right? So this is what power dissipation that we can see here. So what we observe that, so as the power dissipation for this particular network, so whatever we have seen here, okay, the length of the upper transistor pull-up network is 16 lambda, and this one is the same. So we got a less power dissipation, but whereas this value becomes this much value. Okay, why this is happening? So this is what obviously this is what we can say that. So if you are increasing the width of the transistor by something like that, so we observe this kind of thing, the power dissipation will increases. So if you are increasing the width of the transistor, width of the channel, then automatically the power dissipation will increases than that of the length there. So, and here by the by, what is the capacitance, input capacitance? The input capacitance. So the input capacitance is what here at this particular at this place we have to write it. So as we know that 1 square Cc that we can calculate, whereas the input capacitance here is, what is the value? Input capacitance. What is its input capacitance here? It is nothing but 2 times of square Cc that we will be observed. Okay, because that is directly proportional to the width of the transistor. Okay, how much value it is increased there? 1:2 is the value that I have calculated. That means the length is 1 time multiplied and width is 2 times multiplied. So whatever the value that we observe here, whatever the multiplication factor is there for the width, that much input capacitance will increases. That's what we have to understand. Okay, therefore the input capacitance is directly proportional to that of the channel width. Therefore, what is the conclusion that we can draw here? That if the width of the channel, is increases, if the width of the channel increases, then the input capacitance will increases. Input capacitance will increase. Input capacitance will increase. That's what we have to remember for the. So this leads to this was the. This will affect the. This will affect the delay of the circuit. Delay of the circuit. So that's what we can say, that because the RC delay product that we are considering, the capacitance values increases, ultimately the delay of the circuit will increases. Therefore, we have to maintain the proper width. Otherwise, there is a problem with that. Okay. And one more thing is that another problem is that power dissipation is also will increases. So as the width of the transistors increases, what will happen to this one? The power dissipation is also will increases. So therefore, the width of the channel is increases. So the delay as well as the power will be affected. Power consumption of the circuit will be affected. So that's what we have to remember about the device dimensions. So whenever you use the device dimensions, keep in your mind that power and delay must be optimum, or we have to reduce as much as possible. So that's completely depending upon the dimensions of the transistor. Okay, now fine. Let us now understand some points related to NMOS NAND gate. Okay, let us consider an NMOS NAND gate. As we have seen, two input NAND gate. For example, CMOS NAND gate. Sorry, NMOS NAND gate. What do you mean by this one, NMOS NAND gate? What do you mean by this one? That means I'm using the pull-up network is a depletion type mode transistor. Okay, pull-down network is this one. So far, we have seen that a simple NMOS inverter. So what is the dimension that we found previously? What is the dimensions of this pull-up network? 4:1 అనేది మనం find out చేసాం. Than that of this one. Now what happened if the circuit is something like this, like NAND structure? So since we have to talk about output ratio, right? So since these are all the ratio logics, why it is a ratio logic? Because when we apply A is equal to 0, output Y is equal to VDD, we get without any problem. If A is equal to 1 but Y cannot be directly 0. Okay, it's not cannot directly ground value cannot be. It is something like this. So if you want to maintain Y is equal to proper value, we have to adjust the meaningful sizes of both the transistors. Then only it is accepted to connect it in your circuitry. That's the reason why we maintain that 4:1 we have to maintain, so that the succeeding stages are effectively driven by this particular inverter. Okay, so but the scenario is changes here. So therefore the two NAND gates, two transistors are at the bottom. Then what is its dimensions from the bottom to top? So what are the dimensions of I need to consider here? Okay, the question is, you understand this point. So in this situation, a small derivation that we have to do. What is that? Let us first assume. Okay, so in fact, not only this two transistor, it can be n transistors. Okay, let us consider an input NAND gate. Let us consider an input NAND gate. So this is one transistor here, another transistor here, another transistor here, so on up to n transistor. Okay, what we can call this is an input NAND gate. So therefore the two input NAND gate or an input NAND gate scenario is the same. So on up to, suppose some A0, A1, A1, A2, for example, AN. Okay, so the scenario is the same. So what is the scenario is that, let us assume if you want to calculate the ratio, we need to assume that all the transistors are on. All the transistors are on. When it is possible, when all the transistors are on, so A0 is equal to A1 is equal to so on up to AN is equal to logic 1. So then only upper transistor and bottom transistor will be on, and there is a possibility of VDD to ground path will be existed. Then only it is possible to calculate. Okay, so then what is this value then? So what we have to do then? For example, if this inverter, if this NAND gate, for example, let us consider a simple scenario. If this NAND gate wants to drive another NAND gate, for example, other NAND gate as one input to the other one, so that means here the output is very essential for us. Whatever the output that will generated at the first inverter is very essential. So what output voltage when all the transistors are on at the pull down network, when all the transistors are on at the pull down network, the output has to generate what output that we expect, it should be logic 0. Ante kada, what it has to do, whatever the output that is generated from this NAND gate. So at this point, so I'm talking about at this point. Okay, that output must be 0 so that the succeeding stages cannot be on. Okay, so these transistors wants to be off. The transistors off avali anante, what is the V output that must be generated? 0 has to be generated. But what is the minimum condition that we have to do it? What is the minimum condition that we have to maintain? That means whatever the output that is generated should be less than or equal to VT of the succeeding stage transistors, right? So that means whatever, for example, E transistor on. For example, this transistor's threshold voltage ganaka nu takku unnam anukondi output generate chesedi, then this transistor becomes off, right? So this is the condition is very important for us. So this is called critical condition. So this is the point from which we can calculate what is the sizes of the transistors in the NAND gate. In fact, an input or maybe whatever the size of the input it is. Okay, so can you define what is its Vout for this an input device? For example, let me call this is the size of this, the dimensions of this one is n into ZPD. N into ZPD. So length to width ratio of NMOS, all the NMOS transistors. So the dimensions of this one is ZPU, only one transistor. Okay, only one transistor. Okay, so simply it is, how do we calculate the voltage across this one? The voltage across this Y to ground. So therefore Vout is calculated something like this. Vout is actually, it is the power supply VDD. It is the power supply VDD, voltage division formula, nothing else. VDD into n times of ZPD divided by n times of ZPD plus ZPU is less than or equal to VTN of the transistor is usually 0.2 times of VDD. 0.2 times of VDD. So what is its value then? So we can calculate this one something like this. VDD will get cancelled. Under nominal notation, n into ZPD divided by n into ZPD plus ZPU is equal to 0.2 that we can write. Okay, so what is this value then again? So n ZPD, we take it common, 1 by 1 plus, what is this value? ZPU divided by n times of ZPD. Just simply I have taken the common of n ZPD and I have done something like this. Now what is the ZPU divided by n times of ZPD value so that that value is equal to 0.2? That's the question. So therefore by substituting therefore by ZPU divided by n times of ZPD is equal to 1 by 4 by 1. If I take 4 by 1, if substitute 4 by 1 in this particular ratio, then you will get 0.2. Then we will get 0.2. Are you agree with me? So that means ZPU divided by n times of ZPD ratio should be 4:1. We have to maintain. What does it mean? So let us write here. So therefore, what I can write it here, a simple 2-input NAND gate I am going to consider. So this value should be 4:1. It should be there because of this one. In order to maintain that one, what is its value for this one? 2 transistors are in this one. And ఇది మొత్తం రెండు, the bottom transistor రెండు కూడా 1 అయి ఉండాలి, అప్పుడు 1:1 అయి ఉండాలి. సో 1:1 అయి ఉండాలంటే ఎంత ఉండాలి with ratios? So 1:2, and this is also 1:2, right? So what we can say that, for example, 2 input ana anukondi, what we can write it there? What we can say that 1 will be the answer that we will get it there. So therefore the the effective length to width ratio is here is that 1:1 can be possible. 1:1 can be possible if you take that one. For example, 3-input NAND gate you consider. 3-input NAND gate you consider. What is this? What is its value then? Any guess from the class? 3-input NAND gate. This is VDD. This is the ground. So find out that. So what is the length to width ratios for the depletion mode type, enhancement mode type of transistor for 3-input NAND, 3-input NMOS NAND gate, NMOS NAND gate. Okay, so please take it as a homework and do it. Okay. Now, so we have to conclude some points here. Number one, conclusion notes. Number one. See, observe that whenever the number of inputs of the gate is increases, if the number of inputs of the gate is increases, like 2 input, 3 input, 4 input, 5 input, 6 input, like this, if your number of inputs are increases, okay, what we observe that, what we need to observe that, so the series resistance of this transistor will increases. Okay, we observe that the resistance at the pull down network will increases. That means the area of the network is increases. Why the area is increases? Because of the series connection. So I can simply one write point, area is increases. Area increases. How can you say that the area is increases? Is a question. Okay, so as the number of transistors connected in series, the length of the transistors will increases. Okay, that means the size of the series connected devices will increases. So as much the area is increases for the pull down network, that much length must be increased for the NMOS, for the depletion type mode transistor also, in order to maintain the proper length to width ratio for pull down to pull up, to pull down ratio. Okay, so in order to keep ZPU divided by ZPD value PD value correct. So as much as pull down dimension is increases, as much pull up dimension must increase. So as to pull up network. Okay, so anta pull down network anta dimension increase avutundo anta length of the pull up network is also must increases. So that means the overall the area of the network will, area of the circuit will increases. That's the one important point. The second point is that delay of the circuit will increases. Delay increases. So how much delay that is increases, as it is calculated that the delay of the tau of the NAND gate is equal to n times of a simple inverter delay. Why? Because why it is so? So as I mentioned that as the number of inputs are increases, the capacitance values also will increases. That means how much the dimensions of the pull down network is increases, that much dimensions of the pull up network is increases. Okay, so that is directly proportional to that of the capacitance of the circuit. Okay, so therefore, because of the capacitance of the circuit is increases, in addition to the sheet resistance of the material, the delay of the network will increases. Okay, so therefore, when we compare to the simple inverter, NMOS inverter తీసుకున్నాం అనుకుంటే దాంతో పోలిస్తే మనకి n times will increases. For example, 2 input means 2 times of inverter. 3 input NAND gate means 3 times of a simple inverter. 5 input NAND gate, if you consider, 5 times of inverter delay will be increases. Okay, so that is what we can observe. This is because of the diamond, the area required, because this is a completely depending upon the pull-up network area. So therefore, pull-up network as a pull-down network, both areas increases automatically, power as well, area as well as the delay will increases. That's what we should remember. Is it clear to all of you? These 2 points we have to remember about the NAND gate. So therefore, what I can do is that, so for instead of the NAND gate, why can't we go for 2 input NOR gate, NMOS NOR gate? Let us consider the 2 input NMOS NOR gate. Okay, so what we observe here in this case. So here is that a depletion type mode transistor is something like this. NMOS transistor is something like this. But NMOS and PMOS transistors are connected in parallel. Okay, this is what NMOS NAND gate, sorry, NOR gate. VDD, it is connected here, A, B, and Y. Right, so what is happening here? Since these 2 lines, for example, you consider this line is connected to the ground or this line is connected to ground. So that means from VDD to ground, there are the 2 possibilities are there. One possibility, there may be this side it can go, or one possibility is that this side also it can go. Okay, so therefore it is just like similar to that of inverter characteristics depending upon the inputs application. So therefore we observe that it is the same ratio it is maintaining. So 1:1 ratio it is maintaining. It is also 1:1 maintaining. So if the number of inputs of the NOR gate is increases, it does not affect the dimensions of the pull-up network. Why? Because from VDD to ground, you can see different paths are available. So from what we have to observe from VDD to ground, okay, so the path will be the unique path must be existed. So therefore, maybe this path can be possible to go for it, or this path can be go for it. Okay, so at any time, only one particular thing that we can see. At any time, only one particular path that we can see. So therefore, we can say that. So for example, if the A is equal to 0, sorry, A is equal to 1, B is equal to 0, means it's simply an inverter like structure. Okay, it is simply an inverter like structure, right? A is complemented something. So therefore it is, we are maintaining 1:1 in 4:1 ratio. It's not like that the NAND gate scenario. In the NAND gate scenario, all the transistors becomes on. Okay, so for if you want to calculate the on resistance of the device. So here, if you want to calculate the on resistance of the device, not necessary to connect on all the transistors, right? So that's the reason why it maintains the same thing. So therefore there is a restrictions are there in this particular one. So the restrictions are there for the NMOS NAND gate. Therefore, we prefer NMOS NOR gate in this respect. Okay, of course, these 2 cases also we find there is a short circuit power consumption when all the transistors are on, when all the transistors are becomes on. So therefore, when compared to the NMOS technology, NOR is preferred than that of the NAND because of the area point of view, delay point of view, and everything. But as the power consumption is concerned, these approaches are not at all acceptable because we have to concentrate. That means we have to maintain the W/L ratios of each and every device differently. That's the reason why what we have to do, we should maintain the W/L ratios in separately. Okay, so therefore, instead of using this NMOS gate, we use CMOS technology. We use CMOS technology. So the CMOS technology is not a ratio logic; it is a ratio-less logic. So W-band ratio of a pull-up network and pull-down network not necessary to maintain its W/L ratios unless otherwise we specify. Okay, so therefore we are in the next class we are going to see CMOS NAND and CMOS NOR we consider. Already we have already defined, already we have derived that we have drawn the circuits. Just once again we will go for it. And then we will go for different alternative ways are there in CMOS. Also, we will look at in the next class. We stop here today.